Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. Hold on. Why is my system audio lighting up? Every day. Audio issues. I think I don't know what that is. I'll just mute my system audio for now. This should be fine. Or something. Anyway. Dan Colin right off the bat says, have you signed up to Datastorm yet? I haven't yet, but I have the tab open. So I need to do that. Basically, this is just a continuation of the last streams that I've been doing, and I figured that I would do just another demo scene stream today instead of a emulator stream because this week I've actually had work off, and I haven't been doing too much stuff, mostly because I wanted to take a bunch of time to relax as well. But I made a bunch of progress on this SSE stuff, and today I actually am almost done with it. There's a couple more things I want to do, and I figure I could just do them on stream. But basically, the conversion from FPU to SSE code for the synth is done, at least on a branch that I have. And I think it went pretty well. So I kind of want to go over how that ended up looking and some of the changes that I made since the last episode. G. Superland, speaking of parties, hyped for Nova yet? Hells yeah, I am. What is that, in 2 weekends from now, I think? That'll be awesome. In fact, I think I'm leaving in 13 days. I believe I leave on the 20th. By the way, how are you guys in the chat? G. Superland, Daniel Collins, Aquar, Evilak, Wister Toad. Yeah, Evil, actually, it's been the past few episodes that I've been working on this. So let me actually, I'm actually going to pull up the couple things. First of all, I actually want to talk about the results. So the main idea is that using FPU is kind of annoying, but we did that for some linker issues, and I tried to just kind of work around that and ended up with something successful. And the bigger thing that I wanted to get rid of is denormals altogether. Denormals is a particular special case in floating point representation that's used for really small numbers, and they come up a lot in synths because we have a lot of feedback loops. And we don't want them because they're not very useful for us to represent such small numbers, and they're usually implemented with hardware traps that go into microcode, which is definitely not something that we want to spend our time on. Hey, Chief Detector. So the unfortunately with FPU code, there's no way to get around that. You can work sort of around it by inserting places that will like bias numbers and then unbias them, which gets them out of denormal range and then brings them down to 0. But even when you do that, you still have the denormal generated, and then whatever the instruction is that's going to do the bias still has to incur the denormal performance penalty. And we can actually see, I'll show you guys later some of these results between SSE and FPU versions of a bunch of our songs and show you that it tends to be a little faster with the SSE version. And from what I can tell, I looked at a bunch of the disassembly, and I'll show you guys how I did that as well. And it doesn't seem to be the case that, from what I can tell, that there's any auto-vectorization happening, at least not from what I could see. So it all seemed to be, scalars, scalar code with SSE registers. Nothing super fancy, but I believe because we never generate denormals now, I think that's actually why it ends up being faster. So basically what I did is, let me pull up this this commit here. It's on my SSE branch, and I think I just stuffed it all into one commit. Let's pull this up on GitHub here. Now, I know this code isn't public yet, but it will be quite soon, is our plan. This is just one of the things I wanted to look into before release. So the main idea here is that I changed compiler and linker flags where applicable to make sure the VC++ compiler generates SSE code instead of FPU code. Mostly that has to do with just going in the project settings for all the relevant projects and going into C++ settings, code generation, and I believe it's here, enable enhanced instruction set. I have it as not set here, which will allow the compiler to basically do whatever it feels it needs to. Before I had IA32, which would always generate FPU code. We could also do like explicitly SSE2 if we wanted, but it doesn't really matter if this uses AVX or something. So that's basically all that was. Implement workaround for missing SSE intrinsic. So when you have it generate SSE code instead of FPU code, it will generate code that relies, especially if you use math functions, it will generate code that relies on certain implementations of certain functions existing in your standard library. Because we don't actually link to the correct version of the Visual Studio runtime, we use Visual Studio 2013, and that expects MSVCRT 12, I think, .dll to be present. Or at least the generated code normally does, but of course we actually link to no default. We link with no default libraries, so I think is here, and then we supply msvcrt.lib, which is going to link to a system standard msvcrt.dll, which has most of the things that the C standard library actually needs, but not those more advanced math function implementations. So originally I looked into actually implementing those, but I ended up just working around all of them, going through all the usages in the code, which is basically there was one call to cosine and then a bunch of calls to pow, and I just went through and replaced all those with calls to my own implementations eventually. There's some more details about that in some previous streams, but I'll show you guys what I ended up with here. And then finally, remove explicit denormal handling throughout the code base, and then use these particular flags, flush to 0 and denormals R0 flags in the SSE control register to make sure that no denormals are generated or taken as input to the floating point units in the CPU. So that's the main idea, and then the actual implementation, most of it was relatively straightforward. So the first thing, by the way, let's see. The first thing I did is remove these fixed denormal functions. I'll show you what those did look like, although they're gone now. But you can see that these were in a lot of places in the code base. So basically, whenever there would be a feedback loop, particularly, or even just a lot of problematic areas that we found when we were actually writing the code, we would call these fixed denormal functions. And when this was optimized, these ended up being inlined. But basically, we would just bias this by a really tiny amount. So instead of, like, when the number would be so small that it wouldn't be 0, or, I mean, really any number, we would just add the bias always. We should have added and then subtracted it, but I wanted to make sure this wouldn't get optimized. I probably should have looked at disassembly when I was looking at that anyway, but it doesn't matter anymore. But anyway, the idea here is that if it's a denormal number, just biasing it by a very small amount will get it out of the denormal range, and then we're going to have more well-behaved floats. I did one for double too. I actually don't know if you need this. I'm pretty sure that the double representation also has a denormal representation, so I believe you're going to need this, but now we don't anymore. So basically all the usages of that throughout the code are now just gone. The idea is that instead of doing that, we're going to set those flags that allow the SSE unit to basically not handle denormals. Again, the FP unit can't actually do that. There's no way to disable those, which is why we had to work around them the way we did. And I'll go ahead and show you a little bit of that too. The place I ended up setting these flags was in the song renderer, and there's a big reason why I did this. So the song renderer is basically a class that you give it a song and you can call render samples on it. So this represents the entire state of something that can render a song based on the data blob that you give it initially. So it will just deserialize everything, make sure helpers in it is called, which has some global stuff in it, but that's okay for this kind of context. But then whenever you do render samples, we want to make sure of a couple things. First of all, we want to make sure that we get the right flag set for the SSE code. By the way, these are just intrinsic functions that will actually set the different flags that we need to be set in that stuff. And then what I also do is I grab the current value of the register so that I can, as we enter the function, we grab what the value is before we do anything, and then we can restore that on our way out, which helps us be compatible in case anything else has different flags for these or anything. We don't want to just set them globally. And then yeah, while those are set, we do all of our rendering. So this means that the way floating point stuff behaves when called from within this function and when called from outside this function might actually differ a bit. But I mean, this is a 64K synth, and I think that this is more than good enough. Basically, initialization code is going to use whatever it's going to use. It's probably still going to use, because of the compiler settings, it's going to use SSE anyway, but it might have denormals, but that's fine in the initialization code. As long as the rendering code itself is really tight and fast, then we're okay. So that's basically the entire workaround, and then getting the stuff to use SSE, except for those intrinsics that didn't exist. So I ended up actually, instead of implementing the actual implementations that the code would normally expect, I just don't call the math functions for those, and I call my own implementations. So I added pow and pow-f here. And then the only other cosine call was actually done within this helpers thing, so I just added an implementation for that. So if we look at pow and pow-f, they just call fpu pow and fpu pow-f. And also if we look at the initialization thing, it sets up a table calling fpu cause. So if we go up here a bit, I can probably turn that down a little bit. I have implementations of fpu pow for doubles, fpu pow for floats, and these I kind of arrived on over time. Basically, if you search x86 pow implementation, you'll find something along the lines of these instructions. And aside from some range issues and some special case stuff, that's basically all you need. But we do want to make sure that if either of these are 0, there's some corner cases there that we want to handle. So this does some tests like that already. This is also vector call. Because I noticed that when I compiled all the code with SSE, it seemed that like all of the functions that I had were actually compiled as vector call. Just looking at the ways that parameters were passed, like this pointer was always in ECX, and then all of the float and double parameters were in different MMX registers. So I just wanted to follow that because it makes for a lot less register fumbling when you're actually calling this function. Because otherwise, this will actually use FPU code to or we'll actually pass the arguments on the stack and then use FPU for the return value, which just seems really wasteful when we know MMX is going to be used anyway. Especially because some of these compares with 0, I use some MMX functions or some SSE functions because these actually handled basically comparison with positive and negative 0 in a way that I wanted it to. That allowed us to do some less special cases here. This is, of course, not a perfect POW implementation. I think the last thing it does is just it does everything with FPU, but then it unloads it into the MMX registers on return. And then the difference between the float and the POW one is basically just the size of the stuff that it's loading and saving to the MMX registers. But yeah, this isn't a perfect POW implementation, but it does the trick for X and Y being greater than or equal to 0 in most cases that we actually care about. There were a couple things where if X was negative and Y was like an odd integer that we would have to handle. And I ended up instead at the call sites of those, I would just unroll it. So I would just take whatever the argument to the function was and then just multiply it by itself 3 times, which I do fairly often in this code actually. But that was just a fine workaround and should probably be faster anyway. And then cosine, of course, is trivial. Basically, this is also vector call, so we just need to move from the XMM register into the FPU and then call the built-in cosine function and then move out of that again. So really basic stuff. So that's just these basic implementations of these functions. And then I don't think they're called anywhere outside of here, except I noticed that when in the compiled code, these get inlined because they're so small. And then so they end up calling these directly, which is great. And then I was also really impressed with the disassembly of this. This fast cosine gets really fast, but that's something else. So yeah, so basically I had this working more or less after the last stream on Sunday, but as I sat down to start doing proper comparisons, what I ended up doing, I'll show you guys this. No, I have it in a different Explorer window here. What I ended up doing is I built a bunch of our songs. So basically these are a bunch of the songs that we're going to put on our music disc that's going to go out with the release of the synth. So it's Backscatter, Barefaced Cheek, Elysian, Engage, Reverence, Rubik, which is the Soundproof Motion soundtrack, Saber Wolf, and Varia. So a bunch of different tracks that we've done with the synth. And I rendered them with uncompressed using FPU I built executables uncompressed with FPU and then uncompressed with SSE. And then I also did the crunched versions as well, just packed with K-Crunchy. And I took these, and especially these crunched ones, I did some performance profiling on them. And I'll show you the results of the final profiling here. So for example, Rubik, the FPU one, it's kind of hard to see, but if I go back and forth, you can see that the SSE one is clearly, so this is the FPU one and this is the SSE one. The SSE one is clearly faster. And you can't really tell because these graphs are not very good. I don't really know how to zoom into these, especially on the y-axis. But if you look at the number of samples collected, like the idea here with this sampling kind of profiler is that it's going to run the code, and then at somewhat regular intervals, it's going to sample where in the code it's actually running, and based on the symbol information, it can collect where it's spending a bunch of time. In this case, there is no symbol information because this is the crunchy packed one, so all that stuff is stripped. But it will it will actually show disassembly, I think, or not. But that's fine. But what you can see is that So if I run these two executables, which are going to play the same song, so they're going to run for almost exactly the same time, with some variance, of course, just due to how it works with the timers and everything. But if we look at just how many samples were collected over that same period of time, we can see that this one is 146,000, and then this one is 96,000. So this is 2/3 the amount of samples that were collected over the same amount of running time. Drew2 says you can compare reports. That's actually pretty cool. Can I do that with reports from different executables? I actually want to try that. Let's see where this is going to be. Probably just stuffs it in my project folder. But I'm going to try this here. Okay, yeah, this generated a lot of extra stuff here. I think it's this one. FPUN and the SSE one. Okay, so this all basically says the exclusive samples. I guess we can do inclusive samples percentage. Okay, not terribly interesting, but anyway. Daniel Collins says, did you compare Wave versus Wave for the FPU and SSE ones? No, I didn't. That's one of the things that I might do, because as I was doing a lot of listening tests when doing this stuff, and I didn't hear anything that was particularly different. At least not that was like audibly different. I'm sure if we did a wave to wave comparison, then there would definitely be differences, because those little biases that we would add to offset the denormal stuff would definitely have done something, even though we probably wouldn't have perceived it. So anyway, if I did that test, what I would do is I'd go through and I'd render waves from all of them, and then send them to the guys and not tell them which is which, and have them like try to pick it out or something, or which one sounds better. I did that when we introduced the sign or the table-based sign implementation, and the guys couldn't hear the difference, so that was good. And I think that's going to be the same here, so I don't think I'm actually going to do that comparison. But if I do, that's how I would do it. Anyway, the point is that the SSE one seems to perform a lot better. However, the first time I did this on Monday, it actually didn't. It performed a lot worse. And as it turns out, I hadn't actually done the SSE flags correctly. There were two mistakes that I actually made. One of them, if we go back into the song renderer here, which is where this code ended up, one of them is that I think it was one of these flags, because I did it with inline assembler, where I would just load out the register itself and then or it with a couple of the bits set that were supposed to set these bits, and then save it back into the register. And that worked fine, except I had the wrong bits. I had bit 15 and 11, and I did like bit 15 and 6 or something. I don't remember what that was. But then when I fixed that, it still didn't help. The SSE one was still a lot slower, and I couldn't figure out why. So what I actually did is I found out that there's a hot path in here, and you can't see it in here because this doesn't have any of the samples. But if I run this with one that does, which I won't do now because I don't need to, I basically found out that the state variable filter, the next function here is actually a hot path. So if I go in here and just debug this, and I do Control-Alt-D, we actually get disassembly. And I guess I can't zoom in on that. That sucks. But whatever. There. Anyway, I was looking at the code for this, and I looked at it in the SSE version, and I also looked at it in the FPU version. And in terms of like amount of instructions and just the instructions it was using, they weren't very fundamentally different at all. So that wasn't terribly interesting. But then that made me actually suspect that it's denormals again, even though I should have had those disabled. So what I did is I went back into the state variable filter code, and before we had done the SSE stuff, I think there was like here that there was a denormal fix, and then all of these, which were just little feedback loops, had denormal fixes on them as well. So all I did is I added back that bias, so whatever it was, 1E negative 20F or whatever it was, to sort of simulate doing the denormal fix, and then it was fast again. It wasn't as fast as the FPU one, but because this was a hot path, that had a lot to say. So then I could actually play without bugging, which is what it would do before. So then I found out that that was denormals again, and then I started actually debugging it further, and I realized something very, very silly. So what had happened is that in our real-time player here, we create the song renderer on the main thread, and then we create the direct sound render thread. And the direct sound render thread uses this render callback down here to get the song renderer here from the player through this data that's passed through the callback, and then tells that to render samples. Now, the consequence of this is that we create the song renderer on the main thread, but then the song is actually rendered on the render thread. And before I had... no, we want to go to definition here. And before I had this CSR stuff here in render samples, I had this in helpers init. So that would actually be set correctly on the main thread, but then because... Exactly, G Superland. Because all of the FPU and SSE state is going to be per thread when the CPU context switches, all that stuff gets preserved. Then this wasn't actually set on the render thread. So even though I had it set, it wasn't actually happening. So anyway, it was a really easy fix, and I think this is a better place to put it anyway because everything's going to go through this function anyway. That's actually not true. I just realized all of the plugins are going to need to do this too. So I'm going to need to put this in another place as well now that I'm talking about it. So I'm really glad I did this on stream because now I can actually go and fix this. And in fact, I might separate this into a class now. Basically, our VST library is also going to want to do this too. I think VST plug is going to want to do it because device run, whenever device run is called, which I think is just this one, we're going to want to do it. Yeah, so I think we only do it here. And that would take care of everything, actually. Yeah, I'm actually going to fix this while I'm here. Yeah, that's a great debug string. That's the effect name. I don't know how that happened. But this has been forked for like all these. Oh no, this is actually in the VST plug base class, so that just sticks around. That is a funny story that I will never tell on the stream. Let's see. Actually, we can do final references here. Yeah, but it's just that call, and then, of course, all the implementations. So this is where we want to do it. So what I'm going to do here is just take advantage of RII and go into song render. I think I just want to make a new class here. What do we want to call this? I'll actually make it here first because I'm going to be lazy. I like to call these guards usually. Something like that. I can rename this after. Thanks, Chief Detector. I mean, it could be worse. It could be better. But basically, we want to do this. And then we want, that's the type of the intrinsics. So this we want called the restore. And then this will be oops. And then here we can do set CSR, I think. CSR Miami. Sorry. And I think that's what we want. And then here, we're going to do this. Just Superland. I prefer CSR Las Vegas. You know, I don't know. Actually didn't see any of those. Anyway, so this, I think, should do it then. Thanks, Alcama, for the extra approval. I'm generally pretty happy with this code. There's some stuff that's, yeah, anyway. It's working code, so it's not perfect, but I'm happy with it. So this should basically give us the same results. I'm going to do a quick run of this just to see that that's the case. Wonder what song we'll get. Elysian is what we got. Seems to be running at like below 4% CPU, around that. That's a good sign. I'll wait for it to drop, but this should basically not go up a lot. Yeah, we're good. I'm convinced. Yes, exactly, Juicy, that should be. So then I'm just going to split this out into its own files. I'm also going to call this the same thing because who gives a crap. So this is going to be all this. And yeah, I think we no, we don't actually want this in the player lib. We want this in the core because the VST lib shouldn't rely on the player lib, I think. Where's the build dependencies? Yeah, this should only rely on the core. So core is actually where we want this, and that's fine. Because core is meant to have the devices themselves and then all the tools that would be used to build something around this. So this is a fine place to have this. So I'll do this. Core include core, and this will be the .h. And then following the same pattern here, we'll do this stuff. And I know my font's getting real small, but I mean, it's really not that exciting what I'm doing here. It's in song render. So we just want this. And this is fine here. We don't even need the includes for the intrinsics. Yeah, I probably should, Daniel Collin. Fix all those line endings. It's actually really annoying that there's a Windows 1 anywhere. And then we want to do one more thing here, which is I'd like to include all these. Just include it here. Like that. And then the next thing is this last part. So that's here. And this goes in source. And so here we want to that. And then here we just put this stuff. We want these intrinsics here. And we want these. Yeah, I guess Pragma once is cooler than header guards these days, but I think we're good. Does this even need WaveSabre core? I'm pretty sure it does. I'm guessing it will. Maybe I'm wrong, but I don't think I am. And that should build just fine. We should get Elysian. It should be fast. Yeah, that's the same. Cool. And then we wanted to, in here, in VST plug, in this one, we wanted to also do this. So I'll just do this. And then that should apply to the plugs as well. I'm going to be lazy in testing this. I'm going to add a fixed line endings notes to our release plan, by the way. G Superlin, yeah, this does work without new. This is creating this object on the stack explicitly. And then due to scoping here, this will be the destructor will run here, which is what's going to restore the state. This is a really common pattern in C++, as far as I know. And in Rust, you would do the same thing, except you'd put an underscore here so the compiler didn't complain, and then you'd implement drop instead of this. No, it shouldn't. It should know that there are side effects here. So that should basically be it. I'm going to run live, and I'm just going to make sure the CPU usage isn't crazy on some of these songs. I know what to look for the denormal stuff, so. Yeah, at the end of the day, this is still going to be compiled as calling the constructor here and the destructor down here. And then if those functions don't have side effects, then this can be optimized away, but this definitely will work. And if it doesn't, then my C++ is way worse than I thought. But I feel pretty confident about that. I'm actually not going to open the Elysium project because I believe some of these other ones are a lot nastier. Move this over a little so you can see. This is what I'm looking at. And basically what we should see if there's denormal problems is if I stop the music, then this would go crazy, and it doesn't. So I think we're good here. So yeah, I'm pretty convinced about that, and I'm just gonna make sure this is in that commit. So yeah, thanks guys for the rubber duck debugging. Yeah, I should be able to add all of this. So you should see the flyguard stuff added there in the project files. There's the header and the thing, and our line endings are shit. And I won't worry about that right now because I have a note to fix that later. And then here, song renderer only makes the guard. And then VST plug now makes the guard as well. And that should be everything. So now I'm actually just going to amend because this is only one commit anyway. And we should be good. Nice. Always appreciate the extra eyes on the code too, guys. Okay, so that's great. I don't remember what I was talking about now. Yeah. There's our A/B test. The thing that I haven't done still is I haven't done any tests with this in an actual intro. There's a couple other projects that I need to set flags on and stuff. That I just want to try before I call this good. And I think I'll do that. I think I'll re-export Iota and then make sure that works. So I'll probably do that on the stream here. I think this is also going to be a fairly short stream like I've been doing recently, but I think we have enough time for that. I'll comment, not only are you Rubber Duck, you are a Tursock prize Rubber Duck. A gold one. Yeah, I believe that's right, Dinner Colin. About the new doesn't need to go on the heap. In fact, I think it tends to prefer the stack anyway until it has to go to the heap. But that's details of the GC. And then I think structs are always on the heap. Or sorry, on the stack. The other thing we can do, by the way, is I can actually test this. We can actually look at the disassembly for this guard, which I actually kind of want to do. So go in Song Renderer, where this guard is created here. I'm just going to close the other ones. Okay. And here it makes the guard, and we can debug this. And then Control-Alt-D. And here... Yeah, so it actually got inlined here, which actually makes perfect sense because this was going to be on the stack anyway. So it just inlined the stores MXCSR here. And then it should do... Where was this? Yeah, I think the code got a bit messed up here and how it matches up, but we see the normal stuff here. So we're going to see this, then we allocate some space on the stack, store it out, which is going to be our restore value, surely. It may also use that. It loads that into ESI. Some weird stuff going on here. Anyway, okay, so here it stores it out, and then ors it with that flag, loads it back in, stores it out, ors it with this flag, loads it back in. And then does its thing with all the song rendering. And eventually, when it's done, there it loads it back again. So some weird looking disassembly here, but we can see that it actually did do what we expected. And all that stuff got inlined. So that was good. Moliv, thank you so much for the sub. Appreciate it. So yeah. So there we can even see that in the disassembly that this works as we expect. But that's good. It's very nice, actually, to have that disassembly viewer. I've been using that quite a lot the last week or so. Always good to check that kind of thing if you're a little bit unsure. Let's see. So yeah, that is really good that all this seems to work. I wanted to show some of the results of the testing, by the way. You can zoom in here a bit. So this, I just took all the songs and literally just looked at the sizes. So these are the uncompressed sizes of the executables. These don't really matter. This is FPU and SSE. This size doesn't really matter, but I had the data, so I just put it in here. And I highlighted or made in bold, emboldened, is that the word? The ones that were better. So in this case, the smaller ones. Interestingly enough, this is the packed size. And you can see basically the FP one is always smaller. And then sometimes they matched on the SSE ones and sometimes they didn't. When they didn't, it's always 512 bytes larger than the other one. And that actually makes perfect sense because Windows executables, at least nice compliant ones, are always aligned to a 512 byte boundary. And that's definitely what Crunchy's doing. And this is the output from Crunchy directly. So what's going to happen here is that the SSE code is a little bit larger in terms of actual code size. And so it is going to be a little bit larger when it's compressed as well, it seems. And if that goes over the limit until the next 512 byte block, then it just pads up to that. So what this tells me is that it's slightly larger, but basically negligibly so. We've lost at most half a kilobyte here, and it's definitely going to be less than that in an actual intro where more of that can actually be utilized. And then I did the profiling samples collected against all of them, and the SSE one was consistently faster, except on Varia, where the difference was only about 200 samples, which is like nothing. Especially compared to some of these with a lot of variance. This is 2/3 of the amount of samples here, so that's going to be using 2/3 the amount of CPU. I mean, approximately, but this is a metric that I had. So I'm pretty sure we're definitely going to do this in terms of actually using SSE here. So that's cool. And yeah, I think I'll just dive in and do that Iota export now, if I still have all that stuff running, which I should. So let's see. I need to run the demo tool. Let me fire that stuff up. We got to build a couple things here. So I'm just going to do Control-Shift-B here to make sure everything gets rebuilt, although I think we're good there. And then I need to open up another Visual Studio project here. It's kind of annoying to have all this stuff set up the way we do right now, but it's good enough for what we're doing. So I'm just going to go into my demotivation project stuff, and I have a WaveSabre C wrapper project. And this links to the core and the player lib from the other project. So if the other one's built, this will be fine. Here we want to change this because I'm pretty sure in CodeGen I had IA32 here. We don't want that anymore. We want not set, which will allow it to use SC instructions. And I think that's all we actually need to do here. Then we should be able to build that. And this will build it with whatever song is loaded here. I'm pretty sure, I mean, I can't tell from looking at it, but I'm pretty sure this is the Iota track because I'm pretty sure we haven't done any exports since then. And then I'm going to build something called Rivet, which probably has the wrong blob in it right now. So I'm probably going to need to re-export the one from the editor. So I'm actually going to do that first. And actually, we want to do this with and without the SSE changes. So I'm probably going to branch this out and fix that. But I need to pull up the Rocket editor. And just go into Iota sync in Rocket, and then I will run the editor. And that's going to be iota.demo. And that should just work, I hope. Yeah, that's fine. And so then I'm just going to export the project. And here we go into Rivet and source and blob. We say yes. And that looks like it was successful. And my Slack's making noise. And then from there, I'm just going to open up another terminal here. Projects, demotivation Rivet, which is the actual project for this. Or for the actual export, and cargo build release should give us an executable. Maybe one more thing I have to do, but I think I already did that. So we should be okay. And from there, what I want here is target release rivet out.exe. Rivet.exe is the first one. So this is a 264K executable that looks like it runs Iota. We'll make sure. Yeah, good enough. And so this, I think, I'm going to rename this here. So we'll do SSE uncompressed Iota. And I'm going to put that in my SSE tests folder that I had here, along with the other stuff. Where'd that go? Man, I'm so good at window management, you guys. There it is. Or not. Come on. There we go. Put it in there. And then I also want to dash B SSE add that, and that should show us that, which is exactly the change we made. We'll do that, and then we'll check out the last one. Ooh, what's my other commit there? Oh, hook up rocket here. We might want to change that, but that's fine for now. Then we have that ready, and then this will reload, and then we're going to go back to WaveSabre and check out the last branch there, which is an FPU rounding branch that I had previously. And then we're going to rebuild everything so then we have a good comparison. And then I'm going to do some profiling on this. And we should see, I'll just build all. And then we'll go back to the CLib and build that. That should be fine. And then we'll go back to Rivet, and we're going to want to build this again. And we should see a slight difference in file size. We do. It's 64 or 59 versus 50. No, we don't, do we? I'm going to hex edit these, because I really want to compare these. They're identical, so I think this didn't build right. I think we need to, this happens sometimes, that I need to, that the Rust compiler didn't notice that only the dependencies that we linked changed, so we need to make a small change in that code to get this to be dirty. So I'll just open this here. Motivation rivet. And just do something stupid like that. Let's see if that's... Are these still identical? Because I don't want them to be. We can also do this, by the way. Is do a cargo clean. Okay, didn't like that. Just to be sure. Still 259. I want to make sure that these are different. They should be. Although I would have expected a small difference in file size here. Okay, here they're already different. which is weird that they're different before the stub. But I'll take it because they're different. That's all I wanted. And then this one we want to be FPU uncompressed Iota. And put that here too. And then I had another terminal here, this one, where I was doing crunching on all these. So we'll do that too. And in this case, we'll do SC uncompressed Iota. Whoops. C crunched Iota. And we'll run the same thing for FPU. And here we see a difference in the input size and no difference in the output size, which is good. Maybe a larger one would have given us some different results, but I doubt it. So I just want to put these in my spreadsheet here, even though they're the same. So the uncompressed size for FPU, so we'll just do this. $265,216. And the SSE compressed one, or the SSE uncompressed one, that is, 270,336. And of course the uncompressed FPU one is slightly smaller. Who is making noise on my Slack? I don't care. The FPU compressed one, 55808, and if I remember correctly, the SC one was the same. 55808. So those match. And then I want to profile both of these, which is why I made both of them. And before I forget, I'm going to check out this other branch on both of these. Just before I forget to change that back. And then we'll go into here and we'll actually run these. So we're gonna watch the demo twice, both with the FPU one and the SSE one, and we should see that the SSE one uses less CPU. And it should be relatively clear that it does so. So let's go back in here. And I don't know how much symbol information we'll get from running the not crunched ones, so I'll just run the crunched ones. I feel like that's more representative anyway, even though there isn't too much difference. So run this, not full screen with the music, and that'll be good enough. We'll get a little noise from me moving around the window, but that shouldn't be significant by the time the whole demo runs. I saw my task manager running. I don't. I'm going to pull that up really quick. Yeah, a couple more dots than normal Atari demos. Not as much as I had when testing, but because I reduced it on my laptop when we actually made the release, but still happy with it. Runs fast. Yeah, this demo's definitely an encoder killer. Let that finish, and while it's collecting the statistics, we'll just set up the running the other one. Okay. Okay, so we have to wait for it to open this, I guess. That's funny. Yeah, we're definitely missing T-Pulm on the greetings list, aren't we? That's not good. I'll have to fix that. So here, do exactly the same thing, except here we're going to run the SSE crunched Iota. Come on. Come on, Explorer. It's not that hard. There we go. Yeah. Same thing here. Might get some variance from moving the windows around. Don't care about that. Just judging by Task Manager, it looks like CPU usage is a little bit lower already on the SSE one, which is what we expect to see, but we'll see. I won't make that call until we actually see the numbers. Drew, no, I have not. I've not meant to put the emulator progress on hold. I just I've been missing a lot of streams, mostly because it's been a little too hot to stream, especially in the evenings. Yeah, I've been a bit sloppy there. It's not that I'm intentionally trying to do that. It's just how it's happened. Yeah, I'll come. We have an option to pre-render, but it's off by default. Because the pre-render can take a couple minutes. No, GC Berlin, my AC did not arrive yet. Its status has been updated for the order, but it has not arrived. So I'm also quite hot right now. More so than usual. I'm glad you guys like the demo streams anyway. And I think these last few have been really fun, just because this has kind of been exploring something that I haven't really looked into that much. But I think this has been a good experiment, and we'll definitely end up using this, I think. One of those things that it took so much effort to just to test, because I really wanted to test properly. But I think it's worth it. Mainly because when we merge this, we'll never have to worry about denormals again. Yeah, exactly, Hoffman. Hoffman knows this pain really well. As the other synth guy in Logicoma. This is, I don't think anyone's sad to see them go. So while that's processing, I'm just going to get the profiling samples collected for this one. So 1, 2, 3, 7, 8, 4. And for the SSE one, wow, 90,995. If we look at the graphs, you can see a bit of variance in the beginning, and I don't know if that's actually the same stuff or not, because it follows roughly the same pattern. But if you can look at the rest of the graph, you can see it's clearly, like on all this entire range when the demo is actually running, it's clearly less on the SSE one. So that's really good. So this intro ended up being exactly the same size and a lot faster. Again, just to show you the spreadsheet again with this updated information. So that's really good. Now I'm actually super convinced this is the last A/B test I wanted to do before looking into making a PR for this. And then Hoffman, I'm sure, will happily review and merge when he gets the time. So yeah, so I think this is really good. Yeah, exactly, Juicer. But I also think it looks a little bit more consistent in the SSE one, and that would make sense. I don't know where a lot of this performance gains actually come from. I'm guessing it's two things. One, it's probably a bit less register fumbling when it's actually doing like function calls. I think the main thing is that since denormals are never generated, like before they would be generated and then kind of squashed really shortly after, but you'd still incur performance penalties on the instructions that would actually do the getting rid of the denormals. And now that never happens, so I think that also is what makes it more consistent. It's also possible that a lot of this has been vectorized by the compiler, but from what I can tell in the disassembly, that never happened. At least not in any of the code that I ended up looking at, which wasn't much of the code, to be honest, but I didn't see that actually happen. And considering like 99% of the CPU work that happens while this demo is running is the synth, then this actually looks pretty representative. So I'm convinced. Anyway, I think that's all for me for today. There's a couple things I want to do before I make this PR, but I was just going to test another one of the projects, and I can do that a bit later, probably tomorrow. But anyway, I'm going to head out. Thanks, guys, for hanging out, and I will see you next time. Wait. One more thing. First of all, Mullen says, what's the output rate for the music? This is 44.1 kilohertz in 16-bit. But one more thing, I will not be streaming this Sunday. I think I mentioned that on Twitter, but I'm just mentioning it again. I'm going to be out of town, and I won't get back till late, so no stream on Sunday. But I will see you guys next Thursday. So yeah, thanks again, guys, and I'll see you next time.